Predicting hazardous asteroids using unsupervised learning methods. So the problem here that I want to try to solve is, given NASA asteroid data, can I use unsupervised learning techniques to classify asteroids as hazardous or non-hazardous, and therefore screen for hazardous asteroids? The dataset is a dataset that I found on Kaggle. This is the URL here. If you're watching this video on YouTube, it will be linked in the description. If you're watching it elsewhere, I will have made this information available to you, as well as through my GitHub, which you can see the GitHub is linked at the bottom of this slide here. All of these slides will also be uploaded onto my GitHub. So this is the process that I went through. Exploratory data analysis, principal component analysis, agglomerative clustering, k-means, non-negative matrix factorization, and then I'm going to compare the approaches used and make a recommendation for practical applications. So let's start with exploratory data analysis. The initial visualizations revealed a lot of redundancy in the data, most significantly because there were measurements that were replicated in a number of units. There would be a measurement in miles, in kilometers, in feet, and in meters. So what I did was I removed all of the duplicates and kept the units that made the most sense for the measurement that was being measured. For example, lunar distances versus kilometers. When we're looking at how far away something is in space, a lunar distance is usually a little bit more applicable. Constant columns were also dropped. Every single one of them were orbiting the Earth, so we know this, and we don't need to use that in our analysis. They all were tagged with the same equinox as well. I also removed timestamps, and Booleans were mapped to integers. Then I had to do some research, because aphelion distance, perihelion distance, and the semi-major axis are all mathematically related. So I created a correlation matrix to see which one of them could be dropped. And because of the strong correlation between aphelion distance and semi-major axis, I dropped the aphelion distance. The reason being is semi-major axis comes into play in other places as well. So I kept that. More on the EDA. This heat map was the remaining features after that last calculation. And you can see some of these correlations that are still present. And we're looking at the orbital period and semi-major axis, the epoch oscillation and perihelion time, and the Jupiter Tisserand invariant with mean motion. So I did some research on Wikipedia, but also NASA's website, and found that these relationships can be explained by Kepler's third law of planetary motion, for the first one, the mathematical definition of mean anomaly for the second one, and then the definition of the Tisserand invariant, which is also called the Tisserand parameter, in itself. So I dropped the orbital period because it's directly derived from the semi-major axis. I dropped epoch oscillation because it is linearly related to perihelion time. And I dropped mean motion because it's a mathematical derivative of the semi-major axis, again, while the Jupiter Tisserand also, it holds a greater depth of information. There's more you can glean by that factor. And then finally, there's a high correlation between the minimum estimated diameter of the asteroid and the maximum estimated diameter of the asteroid. And that's because of how they're calculated, and that's based on a standard uncertainty due to uncertain albedo in space. And so as a reasonable approximation, I took those two columns and replaced them with a new column that held the mean value of the minimum and maximum for each asteroid. And so this is the final heat map for asteroid features. and I was able to remove those bright yellows everywhere but where they correlate with themselves, which we love to see. And here's some histograms of the feature distributions just so that we have them. It's interesting to note how some of the features behave in different ways as well. But we do see a good number of useful bell curves happening. So here I began my principal component analysis, which the output from it explained the output from my PCA explained variance ratio, and the scree plot showed that 9 components explained 90% of all variance. This allows me to reduce dimensionality to 9, down from, I believe, 15. And after projecting onto my top 9 PCs, I created a table that shows how each component contributes, and it is here on the slide if you are interested. I did want to make a visualization, but it's tricky to visualize 9 dimensions, and I still wanted a plot. So what I did was I plotted the asteroids as projected onto the first 2 principal components. And the red's hazardous, the blue is non-hazardous. And while we're definitely not seeing the full picture because this is only a 2-dimensional slice out of a 9-dimensional space, you can kind of start to already see the red points clustering together in the middle there, which I think is very interesting. So then I move on and start with agglomerative clustering. And so I iterated over a variety of linkages and metrics until arriving at the optimal combination for this particular data, and then arrived at the results. And it turns out the best setup is single and cosine, and we get an 83.96% accuracy. However, my confusion matrix here is heavily unbalanced. Now, that's not to say that it's bad. It could still reasonably represent the reality, because hazardous asteroids are in fact rare, but it is something to flag. Also of note, single linkage with cosine makes sense to have come out as the top performer in this case, as single linkage is sensitive to pairwise proximity, and cosine distance measures angular similarity, which captures directional relationship. Therefore, this setup tends to perform well when clusters differ in direction but have overlapping scales. Likely, this combination captured directional patterns in orbit or velocity features, maybe relative velocity, eccentricity, or inclination, potentially. But just because of the behavior of the asteroid, it does make sense that the single and cosine setup was the best in this case. And then I moved on to k-means, and the results here appear to be more balanced than with the agglomerative approach. As you can see, we have 2 substantial groups present in the confusion matrix. The RMSE also shows the data to be in tighter clusters, but accuracy is lower. And this suggests that the hazardousness may not be cleanly separable by the shape of the clusters used in k-means. Just a suggestion. Then I moved on to NMF, and it's well suited to the asteroid data because the physical qualities measured here in this data are non-negative and can combine additively. Looking at the reconstruction RMSE, which is using the original factors before PCA, the error decreased with rank as expected. When W was clustered into 2 groups to compare hazardous versus non-hazardous, the accuracy was at around 55.6%. I calculated precision, recall, and accuracy from the confusion matrices there and got at rank equals 6. I got a precision of about 0.201, recall of about 0.59, and accuracy of about 55.6%. This shows that while the higher rank captures the continuous physical structure well, but Hazardous is not a distinct cluster inside W. It appears to behave as a threshold over several parameters that are correlated. For rank 2, which was the best rank when I used the same PCA 9 space as prior methods because I wanted to be able to compare them, I calculated precision of about 0.266, recall at about 0.89, and accuracy at about 58.6%. This iteration had a notably high recall, which means that this method is a conservative screen that flags most hazardous asteroids with very few misses. However, it does have many false alarms. Ultimately, with a rank of 6, that would be useful for faithfully summarizing the population. With the lowest, it had the lowest reconstruction error. But rank at 2 with NMF is best for a high recall triage situation that catches most hazardous asteroids, but is slightly less precise and comes with more false positives. So here's a comparison of the approaches used. In this context, the agglomerative clustering was great for finding chains and outliers and exploratory anomaly hunting. However, it had the worst recall and the worst RMSE. In practice, it would not be particularly useful for identifying hazardous asteroids. K-means K-means had the tightest clusters, the lowest RMSE, and it gave 2 substantial balance groups in a fast and stable manner. It does, however, miss some hazards and flag many non-hazards. NMF, with a rank of 2, had a very high recall, showing it has the capacity to capture most hazardous asteroids. It's also possible to actually interpret the physics going on by inspecting H when you use NMF. It does, however, have low precision, which can lead to many false alarms. This method would be best for flagging hazards in cases in which missing the hazard is the worst possible outcome. NMF with rank equals 6 gave the best reconstruction of the data with the lowest reconstruction RMSE. However, it did not have the tightest clusters, and recall and precision were both unexceptional. This method could have some utility in scientific interpretation and dimensional summaries. However, I would not consider it to be a practical method for flagging active hazards. For practical purposes, I would recommend a 2-step pipeline. First, using NMF with a rank of 2 to screen for hazards, and then keeping any asteroid predicted to be a hazard as a subset to be used in step 2. Step 2, then rescore that subset using K-means to achieve a tighter cluster distance. And again, I'm going to show the code for this simulation, but it's available on GitHub. It's public. You can do whatever you need to with it. But here it is. This is just how I ran my simulation code, right? And you can read it on GitHub if you really want to. And then further, these are the results that it gave me. So you can look at stage 1 here, and it had very high recall and showing it catches most of the hazards. Low precision, there are many false alarms, but it is catching most of the hazards. And then stage 2, we are reducing the alerts and boosting our overall accuracy. And the recall does drop to about 51.8%. So there we are. These are my references from some of my data because I needed to learn a little bit more about asteroids and orbiting.